So the title of my thesis is Characterizing and Modeling the Nonlinear Behavior of Additively Manufactured Trapped Powder Dampers. Um, and before we dive into what I've done, I want to give a little bit of background, just what is it that we're talking about and why do we care? So additive manufacturing is a pretty broad term that covers a number of technologies. Popularly, people tend to think of it as 3D printing. Additive manufacturing is, I guess, the more technical term. Specifically, this project is about laser powder bed fusion. And the way that works is you spread a thin layer of metal powder over a surface, and then a laser from above melts together the regions that you want to become part of the final part. And that continues iteratively layer by layer until you finish building the entire part. And additive manufacturing can help you make really unique designs that weren't possible before with traditional manufacturing techniques, where you can take, say, this assembly of a dozen components and reduce it down to a single part, which is really nice for reducing the complexity of the assembly, as well as optimizing for strength to weight ratio or whatever it is that you're interested in. I want to take a detour for a moment to talk about damping and resonance. So here's a schematic of a classic mass on a spring connected to a wall. And if you spend enough time studying vibrations, you start to see these things everywhere. Everything is actually just a mass on a spring to me through my eyes. The car bouncing down the highway, or the airplane wings, or the table that we're in front of. Everything's a mass on a spring to us. And this equation is one that we're familiar with as the ODE that governs that motion, but you don't have to worry about that if you don't want to. It's not important for understanding. So something I want to take a moment to explain is the damping ratio, and that's a term that's going to keep coming up. And you can see in this plot on the left, what I'm showing here is what would happen if you hit this mass with a hammer and let it just ring down until it stops. And if you have a low damping ratio like the blue and orange, it'll keep ringing for a really, really long time. But if you have a high damping ratio like the red and purple, it'll stop very quickly. And it's called damping ratio because it's a ratio of how much damping do I have relative to critical damping, which when the damping ratio is 1, it's called critical because at that point there's actually no sinusoidal component to the solution and it's purely exponential decays. So you need a damping ratio less than 1 if there's going to be vibration at all. And what we're showing on the right is a frequency response function. And this is something that we look at a lot in vibrations. And the way to interpret this is if my input force were sinusoidal, say you had a motor with an off-centered load that's spinning at a given frequency, what would be the ratio of the response amplitude to the input force? And that's what we're plotting on this axis in log scale. So notice something really interesting happens around 10 hertz, which is the natural frequency of this system. And this is what we call resonance, that for a really small input force, you can get really large output response magnitudes. And notice again the log scale on the y-axis. So every time we increase the damping by an order of magnitude, we decrease the response of the system by an order of magnitude as well. So if you're designing a mechanical system and you can increase the damping by a factor of 10, then that means that when it resonates, you'll have 10 times less displacement, which also means 10 times less stress in the part. So this is a really big deal for any system that's subjected to a dynamic load. And you might have heard of resonance with this popular demonstration where an opera singer breaks a crystal glass with their voice. And the reason that's possible is because the crystal glass has a really, really low damping ratio. So coming back to additive manufacturing, something that happens when you consolidate an assembly down to a single part is unintentionally, you dramatically decrease the damping in the system because you've gotten rid of all of those frictional interfaces between parts. So whereas this assembly on the left might have a damping ratio on the order of 1% critical, the one on the right probably has damping something like 0.001%. So 100 times bigger resonance issues if you get rid of all of those interfaces.
John, go back one slide. You taught me something here that I've always thought I knew. Resonance is the magnitude.
I think resonance is the general term for the phenomena.
You said if you change the resonance in order of magnitude, you decrease the amplitude.
Yeah, so if we have 10, if each of these curves is multiplying the damping ratio by 10, and as you increase the damping ratio by a factor of 10, you're decreasing the amplitude of the response. What's
Okay.
plotted on the y-axis is the response over
Okay.
the input force.
Okay, that's,
Or like this, also the stress, I guess.
I'll forget that, but I just learned the definition of it. I would picture in my mind and thought enter, so I just learned it, but I'll forget it again.
Okay, great. Yeah, so people have been looking into ways to increase the damping of additively manufactured parts. And one technique that was proposed a couple years ago that started to draw attention is intentionally leaving pockets of trapped unfused metal powder on the inside of your part. Specifically when you're doing laser powder bed fusion, because you already have this metal powder floating around, and it's really convenient to leave pockets of trapped powder. So in 2018, this group did this study, and this is one of the first ones that drew a lot of attention from the community because they found almost an order of magnitude decrease in the response of the system at resonance. That's what's shown in this table from the fully fused solid beam to the beam that had 3 pockets in it. And that corresponds to, again, almost an order of magnitude increase in the damping ratio that they measured. And since then, a number of groups have looked into this more, and they found a number of interesting things. First, the response is actually highly nonlinear, which means that the amount of damping you get depends on the amplitude of the vibrations. So if they excited the system at a low amplitude, they got a certain loss factor, and they got 3 times that at high amplitudes. And loss factor you can think of as synonymous with the damping ratio. It's 2 times the damping ratio, and they're used almost interchangeably in the literature. And the similar thing showed here in the heat map that the loss factor they measured to be a function of the vibration acceleration amplitude. So not only is it a function of amplitude, but actually the damping in these systems can change over time, which is very concerning. In this particular study, they had one of these parts on a shaker table for a couple hours, and they saw a significant decrease in the damping over the course of their experiment. And they noticed with CT scans that that decrease in damping was accompanied by this appearance of empty space at the top, which means that the powder was settling down. So essentially, the behavior is really complicated and hard to predict, and what we want are models that can help designers to be able to predict how much damping is my part going to have if I put a pocket of these dimensions in this location. So your first thought about how to model trapped powder in a part like this might be, let's simulate all of the little particles of metal bouncing around. And there are a number of people that have done that with something called discrete element modeling, with several hundreds of particles. And typically what's done is you have to assume that the box is rigid and it's translating. And you make a number of simplifying assumptions there, like assuming that the metal particles are perfectly spherical and all sorts of assumptions like that, and decreasing the size of the area that you're studying. This study in the bottom actually simulated several 100,000 particles, which was pretty impressive. It's a rather large simulation, and they got interesting insights out of that. But actually, our parts have millions of particles of metal powder in them. So it's really infeasible to run simulations where you're actually modeling every particle of metal. And this study, they actually did have a deformable powder pocket. And the way they did that was by coupling a finite element simulation of the continuum material with the discrete element simulation of the particles. But you can imagine running those two simulations in parallel that need to talk to each other is, again, very computationally expensive. And what they had to do was scale up the powder diameter to be like 1 millimeter particle diameter, whereas ours is more like 30 micron particle diameter. And that was to make it computationally feasible. A couple of people have proposed on the other side of the spectrum, really simple models like this, where you have just a couple of masses and a couple of parameters to tune so that you can collect a set of data and then find what set of parameters will make this model predict the same nonlinear behavior that you measure. But the issue with that is that it's not clear how to use that model to predict the behavior of something with different geometry. So it's less useful as a design tool. So what we really want is a model that's simple enough that we can run it in a reasonable amount of time and still generalizable enough that we can use it to predict parts that we haven't tested yet. So now I'm going to take a second, step back and explain a little bit about what's been done so far at BYU with trapped powders, and then a little bit about the research group that I'm a part of. So as I was starting my master's, Sam Tang was finishing his in the manufacturing department, and my work really builds off of his. So he designed and printed all of these rectangular beams that have pockets of trapped powder of different dimensions. And he did preliminary testing to measure the resonant frequencies and damping ratios of the first couple modes of all of those. So I've been using the same samples as him and just doing more detailed testing and modeling, building off of his work. So this is our last group photo for the structural dynamics research group. We study vibrations generally, and specifically, we're interested in nonlinear vibrations. And some of the other projects in the lab study systems with bolted joints or with rivets that add nonlinearity in those ways. So my project is able to benefit from that expertise, applying some of the same techniques to experimental testing for nonlinear systems as well as modeling. And this particular project is funded by the NSF, which with a grant that started a year ago. And I've been the only grad student on the project, so for all of the papers that I'm going to present, I did the majority of the writing and as well as designing and leading the experiments and simulations. Okay, I'm going to take a quick water break. I'm getting over a cold, so. All right, so I'm going to quickly summarize this conference paper where we presented our preliminary findings about the nonlinear behavior of these parts. So this is what our test setup looks like. We have the rectangular beams suspended from fishing line that then loops into loops of bungee cords. And the reason we do that is to simulate a very free boundary condition as if it were like floating in space. And we have two accelerometers glued onto the corners, and then we use these instrumented hammers to tap the beam to measure both the input force as well as the acceleration response at the accelerometers. And something that we found is that over the course of an experiment, the damping ratio and natural frequency curves would change. Not only is it nonlinear, but it changes over time. What we found was that if you tapped the beam repeatedly with, for example, with a screwdriver, you could get it to transition to a state that we hypothesize is related to the powder being well packed and settled. And in that state, the natural frequency is closer to being linear. And sorry, I dived in without explaining this graph, but it's showing the damping ratio and the natural frequency as functions of the vibration amplitude. And again, if we had a linear system, these would be constant straight lines.
Different color curves are the different hits each.
Yeah,
Okay.
yeah. So we did 3 tests at the beginning, and then we settled the powder and did 3 more, settled the powder again and did 3 more. Yep. So yeah, so we see both this nonlinearity as well as a shift in that entire curve over the course of the experiment. The next thing we found was that that loss in damping was not irrecoverable, it was reversible actually. If you turn the beam upside down, you would recover that damping at low amplitudes that you'd lost on the previous slides. And if you tapped it while it was upside down, you'd actually go higher than the initial state. So using that understanding of the settling and unsettling, we designed a more complicated study. That work was only studying the first soft direction bending mode of one part. But this next paper studied 6 different beams and 9 modes of those beams. So it's a much larger study. So we used the same test setup as before, where we had 2 accelerometers in the corners, the beams hung by fishing line. And this is just showing the different places that we hit with hammers at different points during the testing. And we designed this experiment where we would intentionally settle the powder and measure all of the modes. And we would intentionally unsettle the powder and measure all of the modes. And we did that with lots of block randomization of the order that we hit the different drive points and whether we were settling or unsettling and which hammer we were using to try to remove all of the confounding variables as much as we could. Yeah, so just to give a flavor for what these data look like, we collected a lot of data. I'm not going to show all of it. But this is for the beam with a 1 millimeter powder pocket in the first 2 soft direction bending modes. And these curves are familiar to what we saw before with an increase in damping with amplitude. But notice that at a given amplitude, there's a wide range of values, both for the natural frequency as well as for the damping ratio. And that has to do with the powder settling and unsettling, as well as other factors like how hard did we hit it and where did we hit it. And not all of the modes behaved the same. In fact, every mode essentially had its own characteristic behavior, and it was really hard to make generalizations. So these are the stiff direction bending modes, so the out of plane, or I guess in the plane, however you want to think about it. And these actually sometimes increased and then decreased, or strictly decreased as opposed to the behavior of mode 1.
And the blue was the first, and then the red is the last one in the set. Is that these lines in here?
Yes, yeah, that's true. And the like transparent envelopes are showing the as if it were a box plot at every amplitude, the first and third quartiles, and then the like lower and upper bounds at that amplitude. And the dotted line is the median. Yeah, and then some of the modes, this is almost linear in damping, but then nonlinear in frequency for the torsion modes. Again, every mode behaved differently. And digging in a little closer, if we separate out the data based on what hammer we used, where we hit it, and what was the powder state, we actually see that variability go way down, and it starts to look very repeatable. So that's something that we studied, is how much do each of these factors affect the uncertainty. We also, in order to show a lot of data at once and the trends with respect to powder pocket thickness, we looked at the summary statistics at a given amplitude. So at the low amplitude range and at the high amplitude range, as well as across the full amplitude range, what was the median, the max, and the min. And that's what is shown in these graphs. So for each beam, as we increase the pocket thickness, the number is the thickness in microns of the powder pocket. So starting from a fully fused beam all the way to the 3 millimeter beam, which was the biggest powder pocket we tested. How does the damping ratio and natural frequency change at low amplitudes and at high amplitudes? For this mode, as we saw before, the high amplitude range pretty much always had higher damping than the low amplitude range. But again, that wasn't the case for all of the modes. So with this data set in hand, we're able to see that for some of the modes, the damping increased by more than a factor of 100 relative to this fully fused powder, or relative to the fully fused solid beam. But that there's many sources of variability that really should be taken into consideration if you want to fully take advantage of this effect. including the powder state, the hit force, and the impact location. And each one of those turned out to be the most important factor for at least one of the modes that we studied. So we couldn't make any sweeping statements about, oh, you can always neglect this or you can always neglect that. And we made a recommendation that people should be careful when testing these parts to account for the powder state somehow, and not just to assume that the part will always behave the same. Okay, with that rich data set in hand, we were ready to dive back into modeling. So we wanted, again, to develop a model that was simple enough that it could run in a relatively short amount of time and still be used to predict new geometries. So our approach to this was assigning a different set of material properties to a region of the part that represented the trapped powder. And essentially what we did is say, what if the trapped powder pocket were actually full of rubber instead of metal powder, or some sort of viscoelastic material like rubber, and then update the properties of that viscoelastic material to match the damping that we see. And the way this is implemented numerically is that you have a complex valued stiffness, where the imaginary part of the stiffness is related to the damping. So this is a linear model, so we get out a single number for damping a natural frequency. So how do we use a linear model to talk about a nonlinear system? The way we approached that was to linearize about a given amplitude range for comparison between experiment and model. So at low and high amplitude ranges, we take the mean and standard deviation across the data in that range for damping ratio and for natural frequency. And these are the samples that we tested for this study and that we modeled. So starting with a full length powder pocket that was 1 millimeter thick. And then that was the model that we used to train the model, or that was the part we used to train the model on. And then we used that model to predict these 3 different parts. And first, what we did actually was to update a model of the fully fused beam that didn't have a powder pocket, just to get a better idea of the material properties of the fused powder. What this graph is showing, we're going to see more graphs like this. On the x-axis is the frequency of the mode, and the y-axis is the loss factor, or 2 times the damping ratio. And the way to read this is, you say, for the first soft direction bending mode, this was the experimentally measured mean and standard deviation of damping and natural frequency. And this was the model prediction. So we got very good agreement in frequencies, less fantastic agreement in damping, but we weren't as concerned about that for the solid beam. We believe most of the damping in these like outlier torsion modes is due to our test setup and the accelerometer wires or something like that. So first we trained the model to match as well as we could the damping of the 1 millimeter pocket beam. And we got relatively good agreement, especially in the stiff direction bending and the torsional modes, which is the orange and the green. And there's something interesting going on that I want to point out in the blue, which is the soft direction bending. So the model always predicts that the damping will increase with mode number for the soft direction bending modes. And that's because higher order bending modes have put more shear in the powder pocket. And the viscoelastic material predicts damping to be related to how much shear is in the pocket. In experiment, however, sometimes we saw something like this, where the second or third mode had more and then the fourth had less. So that's a discrepancy that this particular model is not going to be able to capture. Note, however, at low amplitude that experimentally we did see a strictly increasing trend with respect to mode number, and the agreement is better at low amplitude. And these are the 4 material properties that we were updating and the ranges that we were searching in. Note that there's really wide bounds on all of those properties. from essentially 0 to the stiffness of the fused material. And that's because we're looking at a purely fictitious material. There's not really rubber in there that we can stretch and test to stiffness. So we're just trying to find whatever will give us the best agreement between our model predictions and the experimental data. Okay, so next we had that model and we could use those material properties that we found to make predictions of different parts. So this is the two-pocket beam. And for now, let's ignore the second soft direction bending mode. And looking at the stiff direction bending and the torsion modes, the agreement is actually phenomenal, with almost all of the modes being within one standard deviation of the experimentally measured value in both frequency and loss factor. So we're really happy about that because these are totally blind predictions. We didn't use any data from this beam to train the model that we used to make these predictions. So now, what's going on with the second soft direction bending mode? This beam was designed so that these two trapped powder pockets were located exactly at these red points, which are the points that have the highest displacement in that mode. So for that mode, those powder pockets are being displaced a lot, but they're actually not being sheared almost at all. They're just being translated without being deformed. And because our model gives damping proportional to shear deformation, it predicted almost no damping due to the powder for that mode. But experimentally, especially at high amplitudes, we measured high damping. So this suggests that for that particular mode, the damping is dominated not by deformation of the pocket, but by translation, probably powder impacting the walls. Notice at low amplitude that discrepancy is significantly less in that mode. And we repeated this for the three-pocket beam and for the one with just one pocket in the center, and we saw very similar results where most of the modes line up really well, but there's a couple of soft direction bending modes that seem to not be explained well by the viscoelastic model. So in summary, we developed this model that's able to predict most of the modes, as well as the average change in the damping. And the discrepancies that do exist tell us something really interesting about the damping mechanism. And generally at low amplitude, the match was better than at high amplitude. Okay, so to bring it all together, we collected a rich data set about the nonlinear behavior of trapped powder bed fusion dampers of various sizes. And we documented changes in the damping behavior over time. And we made recommendations about how to account for that. In the worst case scenario, imagine you make a part and you test it and you measure it to have 1% damping, but then you take it out into the field and 6 months later, the powder is settled and now it has 0.1% damping and then it's vibrating 10 times as much. So we really want to make sure that people who are designing these parts are aware of this time varying component that the system can change over time. So you need to make sure that you capture the upper and lower bounds of the behavior. And we developed a computationally efficient model that was able to predict most of the modes very well. And we discussed the insights gained by the limitations of that model. In the future, we would like to look at testing different geometries. So stepping away from simple rectangular beams to something a little more interesting. And then is it possible to design the powder pockets so that the settling and unsettling effect is less relevant? Are there certain cases where you don't really have to worry about it? Maybe a certain thickness threshold, or could you like subdivide the pocket to avoid that? And then are there cases that we can neglect the powder state? Because that would simplify the procedure a lot. And on the modeling side, we want to use our model to predict different beams besides just the 1 millimeter pocket beams to see if it generalizes in that direction. And if it doesn't, optimize, for example, a 3 millimeter pocket beam and a 500 micron beam and look for trends with respect to pocket thickness in the material properties. We also want to apply that model to different geometries once we've tested them. And we have several ideas about how to make our model slightly more sophisticated to capture some of those modes that it currently has trouble with. such as coupling it with an impact damper model, or by developing a fully nonlinear model that captures not just the linearized behavior, but the full nonlinear behavior as well. And with that, I'll take any questions. Thank you.
All right, well, first allow questions from the general audience, including online, I guess, if you want to. Yes, Harrison.
Yeah, I was just wondered, I know you said some previous work had been done, but one of the disadvantages of it was it couldn't be applied to more complicated geometries. So I wondered, with your simplified geometry, do you have a sense about how you compare to them? Like, were you predicting them about as well? Did they have any of the same issues of like not being able to predict certain modes?
Mhm.
I don't know if you have any sense for that.
Yeah, it's a good question. The particular model that I was talking about, let's see, right here in the bottom right, really would, as I understand it, would be able to match just a single mode of a single part. And there's no sense of how to use that to predict a different mode of the same part or anything about a part that was slightly different. So the fact that we're able to make predictions for most of the modes of a part that we don't have any data for, I think is a really significant improvement. Yeah.
Yeah, would any of these other methods be able to, were they kind of similar, just tuning it for one mode? Or did they even get that far, just more kind of what if studies or?
I don't remember having read anything about using discrete elements to predict a totally new part, but you could, in theory, tune it to match one part and then use it to predict a new part. And I think that's part of the appeal is the idea is we're probably capturing the physics decently well, so you'd expect it to be able to generalize.
Okay, so that hasn't been like proven yet or?
Not that I'm aware of.
So they might generalize it by creating a viscoelastic equivalent material, is that the kind of, is that what you mean?
Well, I mean, no, I mean by like using the same model that they like simulating powder bouncing for a part that they haven't tested yet is something that you could do.
Like, so once they've like modeled this one and they've figured out all the interaction properties for the powders and all the parameters in the model, they could go change the geometry and predict theoretically.
Yep, that's the hope of this approach. Yeah. But again, the downside is computational expense, really. And if you're optimizing a design, you really want to be able to iterate and run the model 100 times at least in a reasonable amount of time.
Yeah. Great, other questions, audience?
I'll ask you your homework.
Oh, sure, yeah.
You said the work would be investigating more interesting geometries. What's more interesting?
What could be more interesting than a rectangle?
Yeah.
I like rectangles too. They're
You
nice.
thought about this, I'm just.
Yeah.
What would be more interesting and why?
Yeah, so our first step, we printed a couple of tuning forks that are very similar. This is like our first step away from rectangular beams. It's two rectangular beams connected at the base.
Okay. Connection, all right.
Yeah, and then, let's see, we've talked about like making an I-beam with trapped powder or like a bell or something.
The idea would be like if we could get, something people are actually using in industry,
Well, I look at tuning fork ideas. Can you place powder at different frequency modes to get them to cancel?
That's what we'll see with these tuning forks.
Yeah, I'm really looking forward to testing them. They're really beautiful, and we have them sitting in the lab. We just haven't tested them yet.
Thought you were done and moved on. How long are you gonna stay? I mean, we'll keep you.
Well, I'm looking forward to Jacob doing that.
Oh, yeah. We'll keep you on, I mean.
Yeah.
Okay, I'll be excited to see that. It's just a general question.
All right, one comment from online. Let's see, is this a question or just a comment? Suggestion for the title of your next paper, one damped thing after another, sheer nonsense.
Oh,
Only a family member could suggest
wow,
that, I
that's
think.
beautiful. Thank you.
All right. Okay, well, we'll thank John again and let the audience go. Thanks. All right, and then we'll have the committee grill you for a little bit.